last class we said we are going to continue with molecular orbital theory. Molecular orbital theory proposed to take care of the shortcomings of valence bond theory. It uses mathematical equations to determine the set of molecular orbitals. In this treatment, the electrons belong to the whole molecule. So the orbitals belong to the molecule, means delocalization. The electrons are not localized, they are delocalized because they belong in the whole molecule, not in the atoms. So one of the ways to try to explain molecular orbital theory is by using linear combination of atomic orbitals. Linear combination of atomic orbitals. So linear combination of atomic orbitals, what is it all about? It means atomic orbitals of different atoms add together to make molecular orbitals. So atomic orbitals of different atoms add together to make molecular orbitals. And because molecular orbitals are wave functions, the waves can combine in either way, constructively or destructively. Remember when we talked about constructive wave, they enhance one another, they produce bright light. But when it's destructive, you have that dark spot. So molecular orbitals. Constructive combination of waves results in molecular orbitals that have less energy than the original atomic orbitals. So we can have bonding molecular orbitals which are sigma or pi. Then destructive combination of waves results in molecular orbitals that have higher energy than the original atomic orbital. And we call them anti-bonding molecular orbitals. And we indicate them sigma star or pi star. So these are the two types of molecular orbitals that we are going to encounter. So let's look at it. So interaction of 1s orbitals. So when they interact s minus s, this is a destructive interference and it leads to anti-bonding molecular orbitals. So we write it sigma 1s star. But 1s plus 1s, this is constructive interference. They lead to a sigma bond, and this bond is a bonding molecular orbital. Okay. Let's look at molecular orbitals and their properties. Molecular orbitals and properties. Bond order is the difference between the number of electrons in the bonding molecular orbital and the anti-bonding orbital. Only need to consider valence electrons. We are going to consider mainly valence electrons. And maybe a fraction, bonding or bond order can be a fraction. Higher bond order means stronger and shorter bonds. If bond order equals to 0, then bond is unstable compared to individual atoms and no bond will be formed. No bond will be formed. So these are some properties of molecular orbitals. A substance will be paramagnetic if its molecular orbital diagram has unpaired electrons. We'll say that substance is paramagnetic. If paired, then it is diamagnetic. So how do we calculate the bond order? So mathematically, bond order is number of bonded electrons minus number of antibonding electrons divided by 2. Let's look at hydrogen molecule. So hydrogen molecule, these are the electrons in hydrogen atom. These are the electrons in hydrogen atom. So hydrogen atomic orbital, 1s, it has 1 electron, you see it. So this is the other electron. This is the other hydrogen. So you have 2 hydrogen. Hydrogen 1 and hydrogen 2. They combine to form hydrogen molecules, see? And when they combine to form hydrogen molecule, they form 2 orbitals because they are using s orbitals. You have the sigma, the bonding atomic molecular orbital, because this is the molecule. So you have the molecule here, and the anti-bonding molecular orbital. Because its s is sigma, this one is the anti-bonding, has a star. So each hydrogen brings 1 electron. They put it first in this molecular orbital, which has lower energy. And when they put it, it's finished. Then the antibonding orbital does not have electrons. So how do we calculate the bond order? Bond order is 1/2. These 2 electrons minus 0 equals to 1. So the bond order is 1. Since more electrons are in the bonding orbital than in the antibonding orbital, there is a net bonding interaction between these 2 hydrogen atoms. So there is interaction. There is a bond. A bond is formed between them. Okay. So this is what is happening. So this is the bonding, this is anti-bonding orbital, and this is our hydrogen molecule. So HOM, you don't need to know about it, but it's highest occupied molecular orbital. This is lowest unoccupied molecular orbital. Let's look at helium. These are helium atoms. See? One helium atom has 2 electrons in its 1s orbital. This is the other helium atom on this side. And when they combine, they form helium molecule. We want to find out whether helium molecule can really exist. We want to use molecular orbital to find out whether helium molecule exists. So when they mix these orbitals, these 2 orbitals, they form a sigma, a bonding orbital, and the anti-bonding orbital. Then they start filling them with electrons. They fill these 2 electrons. It's filled. An orbital can take a maximum of only 2 electrons. Then they go to the next one. They fill it and 2 electrons. So let's calculate the bond order. Bond order, 1/2. 2 minus 2. Bond order is 0. And since there are as many electrons in the antibonding orbital as in the bonding orbital, there is no net bonding interaction. That is what our molecular orbital theory is telling us. There is no interaction. And experimentally, there is no hydrogen. There is no helium molecule. You don't have it. It doesn't exist. Let's look at dilithium molecular orbital. So lithium, the electronic configuration of lithium is 1s2, 2s2. No, that's not it. What am I writing? Lithium has 3 electrons, 1s2, 2s1. 1s2, 2s1. So we have two lithium atoms. They mix their s orbitals. This one brings 1 and this one brings, they mix it. They form the molecular orbital. You see, this is the sigma and this is the anti-sigma for the s, for the 1s. Then they go and mix the 2s. They mix the 2s and they form the sigma and the anti-bonding. The bonding and the anti-bonding. Now they have 6 electrons. They want to distribute it in all these orbitals. They start filling. They put 2 here. They put another 2 here. They put 2 here. And this one does not have. Now they want to calculate the bond order. The bonding orbitals have 4 electrons minus these 2 in this anti-bonding minus 2 divided by 2, so you have 1. So it's telling us that you can have this thing. This molecule can exist. That's what it's telling us when you have the bond order like that. It shows that you can have a lithium 2 molecule. Experimentally, let's see whether it has been proven. So since more electrons are in the bonding orbital than in the anti-bonding orbital, there is a net bonding interaction. Any field energy level will generate field bonding and anti-bonding orbital. Therefore, only need to consider the valence electron. So if you look at this, you will notice that because this S is field, it produces bonding and anti-bonding which cancel each other. So most of the time, the inner shells, you don't need to use them. That's what we are saying about stocking. Therefore, just using the valence electrons will give us the answer. So this is what we expect. A lithium molecule. So you have the bonding molecular orbital, which is highest occupied molecular orbital, and you have the LUMO, which is the lowest unoccupied molecular orbital. So interaction of p orbitals. So we have looked at 1s and 2s. Let's look at the p. So when the p interact this way, they form a sigma p bond and these are molecular orbitals, anti-bonding p molecular sigma orbitals. So they are interacting head-on. Then when they interact sideways, they form pi molecular orbitals. Then anti-bonding pi molecular orbital. So this is bonding pi molecular orbital, then anti-bonding pi molecular orbital. See, they interact this way. So let's look at the orbital diagram, including the p. So this is the orbital diagram, including the p orbitals. So these are the atomic orbitals. These are the atomic orbitals from the 2 atoms. These are atoms. Then this is the molecule. So for boron, carbon, and nitrogen, when calculations were done, it is shown that the field electrons in the sigma 2s molecular orbital, then they go to the anti-bonding sigma 2s molecular orbital, then they go to the pi bonding molecular orbital. Then they go to the sigma pi 2p pi bonding molecular orbital. Before they go to the pi anti-bonding molecular orbital, then they go to the sigma anti-bonding molecular orbital. I want you to look at this. These are the atoms. Of course, these are atoms. On this side. But let's look at oxygen, fluorine, and nitrogen. It's different. Here for the S, of course, they fill the sigma S molecular orbital first. Then they go and fill the anti-bonding sigma molecular orbital. Then they go and fill the sigma bonding orbital. Then they go and fill the pi bonding orbital. Then they go and fill the pi anti-bonding orbital before they fill the sigma antibonding p orbital. So make sure you look at the difference. This is for boron, carbon, and nitrogen, but this is for oxygen, fluorine, and neon. So oxygen molecule. Dioxygen is paramagnetic. Paramagnetic materials have unpaired electrons. Neither the Lewis theory nor the valence bond theory predicted this result. So you see, oxygen, it has unpaired electrons. So you see, this is oxygen as described by Lewis and valence bond theory. Look, it shows that they don't have unpaired electrons. It doesn't show the fact that it has unpaired electrons. It doesn't show it. Even this one does not show. You see, paired, 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 paired. But let's look at the molecular orbital diagram for oxygen. So molecular orbital diagram for oxygen. These are the atomic orbitals. They have total 8 electrons which they mix. And remember for oxygen, let me see the periodic table. Oxygen, fluorine, and neon. From calculations of computer, this is how their molecular orbital looks like. So what we do, let's start filling the electrons. We put 2 here, see the 2. Then we put 2 here, 4. We put 2 here, 6. We put 2 here, yeah, 8, 10. Yeah. Then these ones are unpaired. These ones are unpaired. And the bond order is 2. So it shows that there is bonding, then it shows that it's paramagnetic. The unpaired electrons, showing that oxygen is paramagnetic. So bond order, we have 4, 2, 4, 8. 8 minus 2, 4. 4. So 4 divided by 2, bond order is 2. So it shows that oxygen molecule exists, and it also shows the paramagnetism of oxygen. unpaired electrons in the antibonding orbital, oxygen is predicted to be paramagnetic. And oxygen is paramagnetic. So let's draw the molecular orbital diagram for nitrogen and predict its bond order and magnetic properties. Remember, nitrogen is slightly different from oxygen, the way it is. So look at this. The pi is before the sigma. For hydrogen, the sigma was before the pi. So let's look at it. So we have 1, 2, 3, 4, 5. Each of them brought 5 electrons. And so they have 10 molecular orbitals. So we have 1, 2, 3, 4, 5, 6. So 1, 2 for these two. No, they have 8. They have 8. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So when they mix it, the molecular orbitals must be 8. So 1, 2, 3, 4, 5, 6, 7, 8. Good. So now we want to fill them with electrons. So they have 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll start here. We'll put 2 here. We'll put another 2 here. We'll put 2 here. Put 2 here. We have used 8. Then 10. No unpaired electrons. Bond order. 1, 2, 3, 6. 7, 8. 8 minus 2. The bond order shows that you have a molecule. Bond order is 3. But our molecular orbital theory shows that we don't have unpaired electrons. It means nitrogen is diamagnetic. So since there are no unpaired electrons, nitrogen is predicted to be diamagnetic. So I want to thank you again. We've come to the end of chapter 10. So please make sure you answer the odd number study problems, and the answers are found at the back of the book, Appendix 3. So thank you so much. I'll see you next class.